As we've been talking about mechanisms, we've already seen that mechanisms are composed of individual steps. If there's more than one step in the mechanism, we have these individual steps called elementary steps. Now, each elementary step occurs at a particular rate. And remember that rates can be described by a rate law. So each individual step in a mechanism will have its own rate law. Now, unlike the rate laws for overall equations, rate laws for elementary steps can be determined by coefficients or molecularity. But remember, if we're talking about the overall equation, they can only be found by experiment. Now, we've got our table here. We can look at some example elementary steps. So if I've got A producing products, I have a single substance, its molecularity is 1, or unimolecular. My rate law would say that my rate equals K times the concentration of A. If I have A plus A producing products, which is the same as 2A, I have two things interacting. It's bimolecular. We can describe that as a molecularity of 2. And the rate law for that elementary step would say that my rate equals K times the concentration of A squared. I have A plus B producing products, so two particles interacting, molecularity of 2, my rate equals K times the concentration of A times the concentration of B. And then finally, 3A producing products, its molecularity is 3, the rate law says my rate equals the concentration cubed. So if we look at problem 4 from our worksheet, it asks us to look at this table and determine what relationship we see between the overall reaction order and the molecularity. So remember, the overall reaction order is the sum of our individual orders. If I only have one reactant, there's only one order. So for my rate law that says rate equals K times the concentration of A, its order is 1, its molecularity is 1. Where I have A plus A, its order is 2, its molecularity was 2. Where I have my rate equaling K times A times B, they're each to the power of 1. So 1 plus 1 gives me an overall order of 2. My molecularity is 2. For 3A, rate equals concentration cubed. The overall order is 3. The molecularity is 3. So when we're comparing the molecularity and the overall reaction order, they are the same. So then we're asked with problem 5, what do we notice about the orders on each reactant and the elementary step? By that, what we're looking at is if I've got 1A producing products, so right here my coefficient is 1, notice my order is 1. My coefficient is 2, my molecularity is 2, my order is 2. Here, my coefficient is 1, my order is 1. My coefficient is 1, my order is 1. My coefficient is 3, my order is 3. So when we're looking at our elementary steps, the coefficients are the same as the orders. Now remember, when we talked about our rate laws for our overall equations, we were very adamant that they had to be determined by experiment, whether it was the initial rate method or the graphical method. Here we're not talking about the overall rate law. Generally at this point, the overall rate law is already known. It's already determined from experiment. We've used that information to determine what our elementary steps are. From the elementary steps, that's going to give us the rate laws for those elementary steps. So only when you're looking at elementary steps for a rate law can you use your coefficients. So looking at problem 6, we're asked for the rate law of each elementary step in the following reaction. So we're going back to all the mechanisms we've looked at already. Our very first one, we had that mechanism of NO2 plus NO2 producing NO plus NO3. If I were to write the rate law for step 1, the rate equals K times the concentration of NO2 squared, because that's the same as 2 NO2. For step 2, the rate equals K times the concentration of NO3 times the concentration of CO. These both have orders of 1 because my coefficients were 1. With problem 7, step 1, my rate equals K times the concentration of Ce4 plus times the concentration of Mn2 plus. Again, coefficients are 1, so the orders are 1. Step 2, my rate equals concentration of Ce4 plus times Mn3 plus. And then step 3, my rate equals K times the concentration of Mn4 plus times TL plus. So again, the rate laws for my elementary steps, we're just taking the concentrations of each reactant and we're raising them to our coefficients. So then finally with 8, step 1, my rate equals K times the concentration of Cl2. Step 2, my rate equals K times the concentration of Cl times the CHCl3. And then finally step 3, rate equals K times the concentration of Cl times CCl3. So again, the rate laws that we determined on previous worksheets and videos were rate laws for overall equations. We determined those from experimental data. Again, either initial rate or graphs. The overall rate law is governed by the mechanism. The relationship between the rate law and the mechanism can aid us in predicting a reactions mechanism. And so we'll talk a little bit about how this would be done. So mechanisms can be either single step or multi-step. If I have a single step mechanism, that means it consists of a single elementary step. In that scenario, the elementary step rate law will be the same as the overall rate law. So the way we can tell if our mechanism is occurring by a single step or a multi-step, we go in the laboratory, we do experiments. We do that initial rate experiment, or we do our graphical experiment, and we determine our rate law. If we find that our rate law has orders that match the coefficients, then we know our reaction occurs in a single step mechanism. And that single step mechanism, that rate law, tells us what particles are interacting in order to produce our products. Now, a multi-step mechanism consists of multiple elementary steps. The rate law for the overall equation is going to depend on the slowest step. So if I've got multiple steps, I can only go as fast as my slowest step. Now we're going to call that slowest step the rate determining step, or we abbreviate that RDS. If a rate law found by experiment has orders that do not match the coefficients in the overall equation, then we know the reaction occurs in multiple steps. We also know from the overall rate law what particles must interact in the slow step. That determines our overall rate law. So going back to that first mechanism we had. So say we didn't know the individual steps. And we're going to react NO2 with carbon monoxide. And we want to determine the rate law. So we go in the lab, we do some experiments, we determined that the rate law says that rate equals K times the concentration of NO2 squared. So we want to determine, first of all, is this a single step or multi-step mechanism? So we compare that rate law to the balanced chemical equation, to that overall equation. And if I look at here, I can see that the overall rate law has an order of 2, but my coefficient in front of my NO2 is only 1. Additionally, I don't see my carbon monoxide at all. So my orders and my coefficients do not match. The fact that they do not match tells me I have a multi-step mechanism. Now, what this would tell us is that in our slow step, NO2 has to interact with NO2. We could then use that information to predict what our other likely steps would be. Now, at this point, just by comparing our rate law to our overall equation, that tells me if it's single step or multi-step. But to go further, I would need to know how many steps my reaction has and which step is my slow step. So in order to do that, we would conduct experiments in which we generate a progress of reaction curve. So the progress of reaction curve for our mechanism here may look as follows. So we've got our progress of reaction curve in which we have our energy charted on our y-axis. We've got our progress of reaction on our x-axis. So we looked at these before when we talked about our activation energy. So based on what we've seen from previous progress of reaction curves, we're asked, what does each hump represent? Each hump is our activation energy. So remember, on our progress of reaction curves, we start with the energy of our reactants, we end with the energy of our products. The difference in energy between my reactants and this peak here is an activation energy. Now what we'd be looking at is we'd have reactants, they'd gain some energy, they'd produce some products that continue to react. And so we have another activation energy here. Now, next we're asked, what do we think having two humps indicates about the number of steps in this reaction? So we already said that if we've got a multi-step mechanism, each step has its own rate law. And if each step has its own rate law, it has its own activation energy. So having two activation energies on our curve would indicate that we have a two-step mechanism, with this first peak representing step 1, the second peak indicating step 2. Now, if we recall from our previous discussions of progress of reaction curves, when we look at the differences in our peak heights, the different peak heights are going to indicate different activation energies and therefore different rates. So if we compare these two, the activation energy for our first step is much larger than the activation energy for our second step. And remember, we described this activation energy as being analogous to climbing a hill, where higher hills take more time, it takes more energy, and therefore the rate is slower. And so what we would indicate is that the rate for step 1 is going to be slower than the rate for step 2. So from two experiments, we could get a lot of information about our reactions. So again, we could do rate experiments and determine the overall rate law. We compared that overall rate law to the balanced chemical equation. The coefficients and orders don't match here. That gives us a clue it's a multi-step mechanism. We then run a progress of reaction curve. So we measure the energy over time. Based on that curve, we get two peaks. So the two peaks are indicating we've got a mechanism that occurs in two steps, with the first step being slower than the second step. So recall that our activation energy influences our rate constant K. In a progress of reaction curve, the activation energy is the distance from our reactants to the height of our peak. A curve showing only a single activation energy indicates a single-step mechanism. Multiple peaks indicate a reaction occurring in multiple steps, with each peak corresponding to the activation energy for each step. Recall that larger activation energy corresponds to slower rates. So the largest peak on the curve indicates which step in the mechanism is rate determining. So again, we said our slowest step was going to be our rate determining step. So from our curve in question 10, we're asked if the first peak corresponds to step 1 and the second peak corresponds to step 2, which step is our rate determining step. So we already said that step 1 was slower, so step 1 is our rate determining step. And again, from the overall equation, we can identify what particles are interacting in that slow step. So for the reaction problem 9 and 10, we've got the following mechanism. So we've already seen this mechanism. We've already seen the elementary step rate laws. What's different now is that we're being told, and we saw from the curves, that step 1 is the rate determining step. Now, if I compare the rate law for that rate determining step to the rate law for my overall equation, notice that they are the same. This will always be true. The overall equation rate law depends on the slowest step. So if I have a multi-step mechanism and my overall rate law does not include a particular reactant, so it's zero order in that reactant, it's because that reactant does not participate in that slow step. So the example here would be the carbon monoxide. My overall rate law is zero order with respect to the carbon monoxide. That's because the carbon monoxide does not participate in that slowest step. So it doesn't have an impact on the rate. The rate is only as fast as that slowest step. So we can use this, if we have a mechanism, we can use this to determine the rate law for the overall reaction. So we've got a mechanism. Again, this is a mechanism we saw earlier. This time we're told that step 1 is slow. So if step 1 is slow, step 1 is the rate determining step. If step 1 is the rate determining step, then its rate law is the overall rate law. So my rate would be equal to K times the concentration of Ce4 plus times the concentration of Mn2 plus. We have a 3-step mechanism here. So we would anticipate that if we did a progressive reaction curve experiment, we should see 3 peaks, with the first peak being the largest.